although this is what we derived yesterday, I want to remind you something important. A capacitor is a device that, when used, will store a separation of charge. What I didn't talk to you about yesterday, and I'm going to say without proof, is that when a capacitor is connected to a potential difference, the amount of charge that will be stored will be based on its capacitance. So you can just rearrange this to say how much charge is there on a capacitor. Well, that's pretty straightforward. Right? If you know the capacitance, all you need to know is what you connect it to. Yesterday, you were walking around with a 1 farad capacitor. If you connect it to a 6-volt battery in the back, it'll store 6 coulombs of charge, which is actually quite a bit of charge. I would prefer you not discharge that across yourself. So when we talk about how much charge is stored, it's that simple. I'm going to also say, without proof, that the energy stored in that capacitor is equal to 1/2 C, and I'm going to drop the delta, CV squared. I will prove this later, but that is the amount of energy stored in a capacitor. It should be clear to you that you could calculate energy storage in a capacitor more than one way, right? Do you see that there's a clear thing you could use for substitution there? So you could talk to me about the energy stored in terms of charge and capacitance, or in terms of charge and voltage, right? All you have to do is do a couple of substitutions here, and you can have different ways of expressing how much energy is stored in a capacitor. All right? Now, again, we'll prove that in a little bit. What I really want to impress upon you before I talk about cylindrical capacitors, which is not great, is what we mean when we talk about a capacitor circuit. Now, in honesty, what I usually do in talking about capacitor circuits is I lie to you and leave something out. But we have limited days, and I don't know that I have it in me just to do it this way, the same this year. I'm making a simple circuit, and I'm including a circuit element. I did 2 circuit elements I did not talk about. One of them I think is obvious, a switch, right? So what we have here is the symbol for a switch. There are a variety of types of switches and symbols that can be used for switches. You'll see many, but this is the basic look of a switch. Capacitor, voltage source, switch, and this little squiggly line thing is what's known as a resistor. A resistor is a device that prevents is the wrong word, attempts to obstruct the flow of charged particles. So if you have a resistor in your circuit, it tries to slow down the progress of charged particles. I'm oversimplifying what a resistor does, but I want you to understand that there are no circuit elements that don't have a certain amount of resistance in them. So normally I would start without using a resistor in here at all and just say that everything in the circuit happens instantaneously. That's not true. In real circuits, even if there's no additional resistor, there will be resistance in the battery, there'll be resistance in the switch, there'll be resistance in the wires connecting all these things together. Nothing happens instantaneous in a real circuit. Everything takes time. What we're going to find out is that the time it takes for things to operate in a circuit is a critical component of circuit design. You try and make choices that determine how long things happen in a circuit. But for the time being, we're going to use phrases like short time, long time, and immediately. And this is pretty common on the exam. Long time means we get to a point called the steady state condition, meaning whatever you're hoping will happen has happened and nothing is changing in your circuit anymore. Immediately refers to the instantaneous moment you change something. So if I say, what is the value of the energy in a capacitor immediately after you close the switch? Well, I'm talking about the instantaneous moment the switch is closed. That's what they refer to when we talk about those. Short time, that's ambiguous. If they say short time, You're in the middle of a transition. A short time later usually refers to what's happening as your circuit is doing something. So nothing in a circuit happens instantaneously. When I throw the switch here and close the switch, I want you to realize what has happened. We are attempting to connect this potential difference to the circuit elements in the switch, or circuit elements in our circuit. A circuit cannot be created without using both sides of a battery. You have to present your circuit with what the low potential is and the high potential. So in any circuit that we design or any circuit that we do, there has to be a closed loop for all of the items in your circuit. Now, that's an out-and-out lie, and I want you to hear why it's a lie. I said that there has to be a closed loop connecting all of your circuit elements, but we know that the capacitor plates represent an open portion of our circuit. We know that they do, but we still treat it as though this is a closed loop system. We'll explore the openness of a capacitor later, but a circuit requires that both the low side and the high side of your potential difference be used in the circuit. Now, circuits, from the simplest like this to the super complicated, have and use the flow of charged particles generally in some way to manipulate energy. And we're hoping that through the manipulation of that energy, you're able to get to some kind of desired result. Most of our circuits are just going to be real basic circuits. They don't have a whole lot going on, and this one's no different. But in this circuit, there is an interplay between the capacitor, which is like a bucket that stores charge, and the resistor, which is something that is trying to prevent the flow of charged particles. When I close the switch, charged particles are going to flow in this circuit until the capacitor is fully charged, meaning we know what the steady state condition is going to look like in a capacitor circuit. The steady state condition will be this condition in which the capacitor reaches its full charge. That's the steady state condition. So when I close this switch and wait a long time, eventually my capacitor will come up to full charge. A long time in circuit parlance can be milliseconds. I want you to be really aware that a long time doesn't necessarily mean what you think of as a long time. In fact, we'll show how long it takes for most circuits to come up to their full operating position, and it's very short. It doesn't take long at all. We might make a few that purposely take a long time, and by long time I mean 3 or 4 seconds, but a long time in circuit discussions is not long. Everybody got it? Now, for all circuits that we have, there are 2 guiding principles that we're eventually going to call Kirchhoff's laws. I'm going to spell this wrong and don't care. So if you look it up online and you find the correct spelling, please, I can't wait for you to run out and correct me. But I haven't spelled it right for the last 30 years. I'm not going to start now. I will say that I'm bringing them up a little bit early, but it's hard to understand what capacitors are really about until you've actually had a little bit of circuit stuff. The first of Kirchhoff's laws is a conservation of energy law. And it's not, it is the result of conservation of energy. The second law is the result of conservation of charge. We'll talk about the first one, and that says the sum of the voltage drops in any loop through a circuit equals 0. That's what the first law is. I'm not going to write it down. You should write it down. The sum of the voltage drops through any loop in a circuit is equal to 0. That's Kirchhoff's first law. I'm not even sure if they're laws, but they're certainly rules. Since they're based on laws, I guess they're laws. So what that would mean in our circuit is a single loop, right? You understand, right? There's just one loop there. But if you were to start, say, here, and progress through the circuit, the sum of the voltage drops across all the elements in the circuit equals 0. So there's the voltage drop across the EMF minus the voltage drop across the capacitor minus the voltage drop across the resistor. They all sum to give you 0. We don't include the switch. There's no voltage drops across switches. That's all the rule says. And no matter how complicated your circuit is, every single loop in any circuit must obey this principle. The second rule I can't demonstrate with this circuit. Oops, I don't know why I'm erasing that. The second rule is the junction rule, which says that the amount of charge passing into a junction has to equal the amount of charge coming out of a junction. It's about current flow, but I'll say it again. The second rule is about the amount of charge going into a junction and coming out, and that is the amount of charge that goes into a junction has to equal the amount of charge that goes out of a junction. So if you have a place in a circuit where, say, the line splits, the current going into the junction has to equal the current coming out of the junction. We haven't talked about current, but you can probably guess from the word choice that current is the flow of charged particles. So what we would say is that the current into a junction equals the current out of a junction. You're not going to like this, but we use lowercase I for current and uppercase I for current. I know that's not ideal, because what does I have to do with current? I don't know. That's okay. The unit of current is the amp, so we'll use an uppercase A for it. Just get used to this. It's the way it's going to be. I will say this. I use lowercase i's in places where the current is not constant, and I use uppercase i's in places where the current is constant. That'll be a standard thing I will do most of the year. Now, the reason you might be asking me, why am I talking to you about this today? Because your job will be to solve circuits. You'll need to be able to tell me what the result of a circuit will be. How will the energy be stored? What will be the electric potential? What will be the charge on the elements in a circuit? That will be something you'll have to do for me. Did you check that out okay? I don't even know why I bother. So I want you to imagine a circuit that has two capacitors in it. This type of circuit is called a series circuit. The elements are in series. Not to be confused with a parallel circuit, where the elements are in parallel. So here's a parallel circuit. It should be kind of, I didn't put a switch in there. Let's put a switch in there. No matter how complicated your circuit is, you should be able to use Kirchhoff's laws to figure out how each of these circuits behaves. And what I mean by that is, to solve a capacitor circuit, I'm expecting that you could tell me the voltage and charge that are developed on every circuit element in your circuit. You should also be able to tell me the energy on individual circuit elements and the total energy stored in the circuit. Now, for the time being, we're just going to be looking at an overview of circuits and what we can do with them. But capacitors store energy. One of the more interesting things about a capacitor is that after the switch is closed in a capacitor circuit, and we've waited a long time, meaning we've waited long enough for the capacitors to become fully charged, when we open that switch back up, the energy that is stored in the capacitors stays in the capacitor for later use. In an ideal world, a capacitor will remain fully charged for the rest of its usage until you discharge it. In fact, one of the things we'll do in labs is make sure that we discharge our capacitors before you store your circuits, because they can remain charged for a long time. Now, I want to examine for just a minute, and I don't really want to talk about it this way, but I think if I don't, I will have issues. So let's take those 6-volt batteries you have in the back and connect it to a 2 farad capacitor. And why don't you take a moment to just practice a little bit of real quick stuff. What would be the charge on this capacitor and how much energy would be stored on this capacitor? Just take a quick minute for you to do something rather than stare off into space. So again, we have C times V, which is going to give you 2 farads times 6 volts, which will be 12 coulombs. A farad is still coulomb per volt. And 1/2 CV squared, so 1/2 times 2 times 6 squared, giving you 36 joules. Now, what I would really like us to do is deal with this circuit. Let's do the generic circuit first. So I have a potential difference applied to capacitor 1 and capacitor 2. And then we'll do pragmatic. Let's assume capacitor 1 and capacitor 2 are not of the same value. I'd like to use what we talked about with Kirchhoff's laws to figure out how much charge 1 is and charge 2. And maybe go further and say what is V1 over the first capacitor and V2 over the second capacitor. This is solving a circuit. What we're going to do is produce a repeatable result, something that we can use without using Kirchhoff's laws. Kirchhoff's laws are like Newton's laws for circuits, in that they are the absolute hardest way to have to deal with the circuit. We will attempt to always find a shortcut rather than using Kirchhoff's laws if we can. But Kirchhoff's laws are the absolute hardest way to have to deal with the circuit. They work in every circumstance. But if you paid attention, Kirchhoff's laws generate at minimum 2 equations per loop. One equation for the flow of charge and one equation for the voltage drops. The more complicated your circuit is, you're going to start getting lots and lots of equations really fast. They're all linear equations, but you can have a system of 10 to 15 linear equations for what looks like a super simple circuit. So half of the second chapter of Diffenderfer is all about finding ways not to use Kirchhoff's laws. And they have a ton of other ways around it. We're going to try and produce some straightforward, repeatable results. But we're going to use Kirchhoff's laws first. First law is the sum of the voltage drops across all the elements in the circuit equals 0. Now, I'm going to give you a little secret here. You can choose the direction that you draw your loop. I can choose to draw my loop in this direction, or I can attempt to draw my loop in that direction. Here's a hint. When using Kirchhoff's laws, draw your loop so that you go from the small side to the big side of your battery. If there's more than one battery, you may not be able to do that. But if you can, small side to big side. The reason is that when you go from the small side to the big side, that is a potential increase. So you don't subtract the battery, you add the battery. But every other element in a circuit, you're likely going to be subtracting. And that's because it's a voltage drop. I mean, consider what would happen if you were to actually connect this circuit. This is the positive side of the battery. This is the negative side of the battery. The negative side is going to attract protons from this capacitor, making this capacitor become negatively charged. The positive side of the battery is going to attract electrons from that circuit, making that plate positively charged. And in the middle, The positive charges are going to drive away the positive charges from this plate and send them to this plate. So in our circuit, this is going to be the polarization of our capacitors when this circuit is connected. Please understand this, because one of the things we will do is we'll take apart circuits after they've been charged and rebuild them, and you'll have to pay attention to the polarization of the capacitor. So when we close the switch and set up a circuit, this is the arrangement. Now, I want you to think about something real quick. There's clearly going to be a voltage drop across each of these capacitors. And that's going to be the voltage drop across capacitor number 1 and the voltage drop across capacitor number 2. And that has to sum to be equal to 0. This is conservation of energy. Whatever energy you put into your circuit, all of the circuit elements in that circuit will utilize that energy. That's how you apply the law. If we had drawn our loop in the other direction, it wouldn't look much different because we would have an increase in potential across these elements and a decrease in potential across that element. So when dealing with the potential drops, you have to be careful to understand whether your element has an increase in potential or a decrease in potential. So I said you add up all the voltage drops, but a voltage drop can also be a voltage increase. The next law is the junction rule, which had to do with currents, but it also has to do with charge. And it's important to realize that there's only one loop here. In this one loop, whatever amount of charge is placed on the first capacitor has to be the same amount of charge on the second capacitor. They're in series. If one electron is pulled from the top plate, that means one proton has to be pulled from the bottom plate, or one electron added to the bottom plate. That means only one electron could be exchanged in the middle. So Kirchhoff's second rule creates a unique condition for capacitors in series. Capacitors in series will all level off to the same charge. I would strongly encourage you to write that down before you walk out. Capacitors in series all level off to the same charge. And we're not quite done here, but we got a lot of what I wanted to get out done.